Greetings and welcome. In this session, we will see how to solve a numerical on equal friction method of duct sizing. So there is a concept of duct design. In a central air conditioning system, ducts are used for carrying the air, conditioned air between the different locations. So in that case, here if you see, these are the images. Here you can see the shape of this. These are the air carrying ducts of sheet metal, and these are used to convey air from the main air handling unit to the different locations of the room. So here if you see, this is a room side where the air comes out. So this is a outlet, we call it as a slot diffuser. So in this case, the size of the duct means this is a rectangular shape. Normally the duct shape is preferred as a rectangle. So rectangular cross section, so that size, longer side is a A and other size is a B. So that size is to be decided. And again, if the duct is a circular, so in that case we have to find the diameter of that duct. So there are different methods of finding this in a duct design. So one of the method is equal friction method. So numerical based on this we will see in this video session. Let us see a statement of the numerical. So in this numerical here, using equal pressure drop method, estimate the diameter and velocity pressures in AB, BC, CD, BCF duct sections. So this is a flow diagram of the air passing through the duct. This is a fan location A, and these are the different duct sections as mentioned here: AB, BC, CD, BE and CF. Length of these sections are mentioned over here, and these are the outlets, 3 outlets. So outlet E, D, F, and at the outlet the available air flow rate in a cmm means cubic meter per minute, that is meter cube per minute. These are mentioned here. Velocity in a main duct AB, that is mentioned 600 meter per minute, and density of air is asked to take 1.2 kg per meter cube. So in this numerical, now first of all we will find the sizes of the duct, it means diameters, and velocity in sections, these sections, and then we will see about the velocity pressure. That is the second point, velocity pressure. So for that, first of all, let us go to the table. For this we need to have some table. In that different columns we will use. So here we have enlisted the data which is given in the statement. Density of air is given 1.2 kg per meter cube. In a main duct section means AB, velocity is given 600 meter per minute. This velocity we have to convert into meter per second, so divided by 60. So thus we get 10 meter per second. After that we have to find discharge in a main duct. So we have to start from section AB. So for that we have to find discharge first of all. So section AB, in that QAB means discharge passing through this main duct. This will be what? Discharge which is distributed to these different sections. Sum of these 3 means QE plus QF plus QD. These 3 discharges, 120 plus 160 plus 200. So that comes 480 meter cube per minute, because all these discharges or volume flow rates given in cmm. Cmm means meter cube per minute. Cubic meter per minute means meter cube per minute. So this also we have to convert into meter cube per second. So for that, again dividing it by 60, then we find here 8 meter cube per second. So here we find this QAB, discharge in main duct. Now we have the two values. One is a discharge and another is a velocity for this AB duct. So this here in this table, now we have to write the values which are known to us. So now here these are the known values which we have written. These values are written in meter cube per minute and these values are written in meter cube per second as per the given data. Now we have to find all the values which are here of the cells which are here empty cells. So for that, the method which we are going to use, that is equal friction method. So for this, now we have to use friction chart. So let us go to the friction chart. So in this friction chart, now we have to take help of the two values. First value is a Q value in a meter cube per second. 8 meter cube per second value is given, we know, and velocity is a 10 meter per second. So now these are the velocity lines. If you see here, these are the velocity lines 2, 3, 4, 5, 6, 8, and here this is a line I am showing here with this pen. This is of 10 meter per second velocity. So line intersection of the point of the two lines, one line that is from 8 value in horizontal way, and this is inclined. So here we will find this point. So this point, for this point, now we can find the other value. That other value is what? These are the diameter lines that already we have discussed in a friction chart video session. So these are diameter lines. So here through this point which I have pointed here, 1000 mm diameter line is passing through this point. So diameter for this duct AB of the in a mm, that will be what? 1000 mm. And if you project a line from this point in a downward direction, so here you will find 0.1, this value. This will be what? Friction loss in mm of water per meter. So this will be value of PF. So let us now enter these two values in the table. So we have find value of PF, that is a friction, PF, that is a friction loss in mm 0.1, and diameter we have obtained from the friction chart 1000 mm. This is for the case AB. Now here we have to find velocity pressure. So for that we have to do the calculation, and again we have to write statement for these two values also. So that is why we will take here next page. So here we will write from friction chart for Q is equal to 8 meter cube per second, that is a discharge of AB duct, and velocity of AB duct, that is 10 meter per second. We get first is what? Friction loss, that is PF 0.1 mm of water per meter, and second we get diameter, that is of duct AB 1000 mm. And then the next calculation is of velocity pressure. So velocity pressure, that is a PV. For this we have seen in a some video session. Formula is what? Rho v square by 2. Rho a means density of air that we are given, that is 1.2, and velocity that is obtained here from the given data, that is 10, and we have to do square of this 10 divided by 2. So if you do this calculation, then we find the value 60. As this is a dynamic pressure, PV is a dynamic pressure, another name is what? Dynamic, because it helps to move the air or to give the velocity to the air. So that is why the name of the pressure, velocity pressure or dynamic pressure, and it is mentioned in the unit Pascal, that is Newton per meter square. So in this way we have done the calculation and we have received all the values for section AB. So now here we have completed this AB duct. For this, these are the obtained values from the friction chart: PF, diameter and velocity pressure. Now the same method we have to repeat for these further duct sections. Now if you see the duct BC, so for duct BC here, the volume flow rate which is passing through this BC duct will be what? These are the two outlets which are after the BC duct section. Means for the duct BC there will be what? Summation of these two volume flow rates, that will be Q of BC. So now under the section, so for the section BC, first calculation will be what? Discharge passing through this duct BC, that will be summation of duct CF and duct section CD. So these two discharges are given. CF is given 160 and CD is given 200. So total comes 360 cmm, meter cube per minute. This we have to convert into meter cube per second. So we found discharge through section BC, that is a 6 meter per second. Now this we have to enter in the table. So here 360 cmm in this column, and in meter cube per second 6. Now the further process in that, as the name of this method equal friction method, means what? Here this column, in this column now for all duct sections we have to keep friction loss same as per this method, because the name is equal friction method. So for this we can write at all locations 0.1 value. So let us write this value. Now we have here for other sections BC, CD, BE, CF. Now we are having availability of two values. One is of discharge and second PF. So by using the friction chart and taking the help of these two values, getting intersection, as we discuss how to use the friction chart, we can find the value for velocity and diameter. So that do. And after that, we can calculate velocity pressure by putting the value of velocity in the formula. So this we will do for the section BC now. So keep PF 0.1 mm, same for all, and here QBC. Now from friction chart, means you can draw a small diagram. Here you can take PF, so you can take here cross section of this Q and PF value. So Q is here 6 meter cube per second and PF is here 0.1 mm. So combination of these two on the friction chart, you will find this intersection point, and through this intersection point, if you draw a line like this will be line for diameter, and if you draw this line, this will be line for velocity. Now from the friction chart, if you do this homework, then you find the diameter from the friction chart 900 mm. So diameter for this BC from the friction chart we find 900 mm, and velocity that we find 9.5 meter per second. Now this velocity you can use to find the value of PV, that is dynamic pressure. Rho v square by 2, 1.2 into this 9.5 square divided by 2. So this calculation comes 54.15 Newton per meter square. So in this way, under the section BC, we obtain the two values from the friction chart, that is the diameter and velocity, and one value by the calculation. Now these three values we have to enter in the table. So here now we will enter these values. So here is a 900 diameter, and velocity we find 9.5, velocity pressure we find 54.15. So we have completed section BC. Now take the section CD. Now in a section CD, if you see, here is a discharge which is available, that is at the end 200 cm. For 200 cm discharge, and friction, that is a PF value 0.1. So let us go for the next process using the friction chart diagram. So in a section CD, for CD section discharge 200 cm, that is in a meter cube per second 3.33, and PF value 0.1 mm. By using friction chart, intersection point obtained by using these two values, and through that intersection point, then finding the values of diameter, we find the value of diameter 725 mm, velocity we find 8 meter per second, and this dynamic pressure we calculate by putting the value of velocity, that comes in a Newton per meter square. Now these values we have to put in the table. So 725 mm that is a diameter, 8 meter per second is a velocity, and 38.4, that is a velocity pressure. So we have covered the section CD. Now let us follow the process for section B. Now in a section B, if you see, this is a outlet. At the outlet here the discharge available 120 cmm. So 120 cmm means 2 meter per second. So combination of discharge 2 meter per cube per second and PF value 0.1. By using friction chart, let us find the values and write in the table and also in the text. So under section B, here for the discharge B 120 cmm or in a meter cube per second, that is a 2, and value of PF 0.1 we get from the friction chart by the application of these two values and getting intersection, and then passing through that intersection, finding the line for diameter and velocity. We find the diameter for the section B 600 mm and velocity we find for B section 7.2 meter per second. Using this velocity value in this formula, we find the velocity pressure in a Newton per meter square. So putting these values in table, velocity we find 7.2 meter per second, diameter value we find 600 mm, and velocity pressure we find 31.1. So we completed section B. Now the remaining section is a CF. Let us go for the section CF. So here, if you see the CF section, this is a 160 cmm, that is a Q value available in meter cube per second 2.67. So by the combination of 2.67 and 0.1 from the friction chart, let us find the value of this velocity and diameter. So under the section CF, the calculation part for QCF, as from the diagram, 160 cmm discharge is available at the outlet in a meter cube per second, that comes 2.67. As per the equal friction method, PF value we take same, that is 0.1. From the friction chart, for the combination of these two values and getting the intersection point, passing through that intersection point, other two lines, one is for the diameter. So diameter value we get 670 mm, and velocity line passing through that point, velocity value we get 7.75 meter per second. Using this velocity value in this formula, velocity pressure we find 36.04 Newton per meter square. So let us write here in the table. Diameter we find 670 mm, velocity we find 7.75 meter per second, and velocity pressure by the calculation we obtain 36.04. So in this way we have completed the all values in the empty cell by using equal friction method. Now the remaining part is what we are asked to find the maximum pressure drop which occurs in this duct system. So for that we can go to the main diagram. So here this is a main diagram. Here if you see, these are the lengths we are given: AB 30, then here is a 20, here is a 30, and here is a 20. So here we can have different paths, and out of these different paths we have to identify the path length, maximum path length, the path of maximum length. So here we if you see this path AB, BC, CD, so total length of this will be what? 30 plus 20, 50 plus 30, that is 80. If you follow this path AB and B, that will be what? 30 plus 20 means 50. If you follow this path AB, BC and CF, then will be length what? 30 plus 20, 50 plus 20, 70. Means among these three paths, the maximum path length is for the duct section AB, BC and CD. So let us take that maximum path length in the consideration. So maximum path length Lmax will be what? Length of duct AB plus BC plus CD, 30 plus 20 plus 30, that is a 80 meter. Now we are asked to find maximum pressure drop. So maximum pressure drop which occurs in a duct system, that will be equal to Pf value into Lmax. So here we have obtained from the friction chart 0.1 mm value, that is for 1 meter of length, and we have here total path length is 80. So maximum pressure drop will be what? 0.1 multiplied by 80, so that comes 8 mm of water. So in this way, in this numerical, we have seen how to find the diameter for the different sections of the duct, then velocities through that duct. Then we have calculated dynamic pressure values for the respective duct sections. After that, we discuss about how to find the maximum path length, and by using that path length, then we calculated maximum pressure drop.